Earth starts to get an oxygenated atmosphere by 2.2 to 2.5 billion years ago. The evidence is varied and is based on geological observations basically as follows. First, we have unstable minerals that dissolve in an oxygenated atmosphere. These include sedimentary uraninite, which is uranium oxide, siderite, an iron carbonate, and pyrite, iron sulfide. When we find these minerals as pebbles in sedimentary rocks, the implication is that there is not enough free oxygen around to destroy them. All are found unoxidized in sediments older than 2.3 to 2.6 billion years ago, but none afterwards. Pebbles of pyrite, for example, do not occur today in stream gravels, but once they used to. Indeed, today sulfide ores can melt in open air, creating sulfuric acid and eating holes in things. This happened to the desk in my office when I left a chunk of massive sulfide ore exposed to the sea breeze. Here's what the sample looks like today. Okay, there's my bag of sulfides, and this is one of the larger lumps of it in here. Okay, so what happened was that I put a lump of sulfide on my desk, okay, this one, and I forgot about it. A couple of months later, while cleaning out my office, I discovered the sulfide lump under accumulated papers. It had a big black ring around it, and the acids from the combination of the sulfide rock and the air had eaten right through the top of the finish and into the plywood underneath. I have now gone through several generations of plastic bags eaten by the acids, as my sample has gradually oxidized over the years. Another line of evidence for an oxygenated atmosphere is the first appearance of red oxidized soils. These are called red beds, and the first ones appear sometime before 2.2 billion years ago. The exact age is not known because the dates come from intrusive dikes and sills that cross-cut the soils. Therefore, the dates are for rocks younger than the red beds themselves. This is where the 2.2 billion year old date comes from. A third line of evidence is the diversification of stromatolites. Stromatolites become much more diverse in terms of their size and shapes after 2.5 billion years ago, suggesting diversification associated with oxygenic photosynthesis and perhaps with eukaryotic communities. A fourth piece of evidence are banded iron formations, or BIFs, that I have mentioned before. These become common between 2 and 2.5 billion years ago. They contain 90% of the world's iron supply. Virtually all of our steel-making industry depends upon these deposits. Banded iron formations form when ferrous iron, that is Fe+2, is oxidized to become ferric iron, Fe+3. Ferrous iron is soluble in seawater, but when the ocean starts to accumulate some free oxygen, the iron rapidly oxidizes to insoluble ferric iron and sinks as iron oxides to the sea floor. The layering in banded iron formations suggests there may have been waves of precipitation of iron by reaction with free oxygen produced by cyanobacteria. Notably, the deep oceans were probably free of oxygen for more than 700 million years or more after the first whiffs of oxygen became detectable in the atmosphere, since we continue to find banded iron formations up to around 1.8 billion years ago. At that point, they become rare in the rock record, suggesting that the ocean had become too well oxygenated to have very much ferrous iron dissolved in seawater. The last piece of direct geologic evidence comes from glacial sediments deposited during a massive glaciation around 2.5 billion years ago. What's the connection between an oxygenated atmosphere and glaciation, you ask? Well, when the atmosphere starts to accumulate oxygen, the oxygen assaults methane. And methane is a powerful greenhouse gas that gets oxidized to carbon dioxide. That in turn dramatically reduces Earth's complement of greenhouse gases and plunges Earth into glaciation. Now, the glacial sediments are varied, but some very distinctive lithologies are first of all till, basically the unsorted rubble plowed up by a glacier, and the presence of drop stones in marine beds. The till is easy enough to understand. Moving ice is like an inexorable force, and like a bulldozer just plowing up everything in its path. Till, which is also called diamictite, is the result. A completely disordered sediment with angular bits of local rock types, finely ground glacial flour, and everything in between. The dropstones are another great bit of evidence. These are pebbles to boulders that get frozen into the base of a glacier. When the ice calves into the ocean and makes icebergs, the rocks go along for the ride. When the ice melts, the rocks are dropped into deep water, usually landing in fine, goopy mud, clear evidence of ice transport. It turns out that 2.5 billion years ago is a banner time for glacial sediments, suggesting an abrupt onset of glacial conditions when the atmosphere first became oxidizing. So, in summary, there's lots of evidence that the first whiffs of oxygen became established in the atmosphere by around 2.5 billion years ago. Now, the next question is why?